Hi, hello, and welcome to section number 3. Woo. Yes, I think, to me, this is the most important section of the whole class, where a lot of what we're going to be doing today is kind of picking up the pieces from yesterday. How are people feeling after lecture 3?
I thought it was going to be worse than it was.
Hey, I mean, if we tell you to expect trauma and it's like, oh, that was a little T trauma, not a big T trauma. I would say going around during lecture, at a certain point, I saw hands moving and I saw your eyes, but the lights were on and no one was home. And it was just kind of like, yeah, like after about an hour, I saw people get overwhelmed and then it's just like in your head, you're doing the hymnage, like dun 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 dun, where there's just like, who knows? And so a lot of today's section is kind of like, what was that? Like how, if we're going to be learning a lot of reactions, what are tools to help us study reactions? But before we get into all that, scan the QR code for attendance. The fun question today is, what's the song of the summer? Or what's your song of the summer? If you do respond to it, I will be compiling them into a Spotify playlist and sending it out. So that's fun and exciting. Leave your mark on this playlist. I also want to give a heads up that I'm going to be sending out a scary announcement. I'm so sorry. It's one of like 3 scary announcements the whole time. The first scary announcement was the super long one I sent at the start. Yeah, the test is in 8 days. But the scary announcement that I'm going to send out late tonight is going to be about practice exams, we are going to hand out print versions of the practice exams during lecture tomorrow. And we recommend you use the print version because the exam is on paper. But the scary email will be essentially about how to approach the practice exams in ways that will help you when you're studying. And particularly, you're going to get the practice exams tomorrow. Do not look at them until you are done with the problem set. You really need to kind of think about the timeline of studying because you're going to have a problem set due on Monday, and then you're going to have all of 2 days and then the test. And so it's like, how do we balance the problem set, the practice exams, studying, all the things. But yes, it uses some harsh language at one point that says something along the lines of like, if you don't do this, you might as well just drop the class, which is not my words. I'm quoting Logan from previous years. I contextualize. I say like, this is kind of harsh, but the sentiment is true. So again, scary email announcement coming out. Apologies. Also, there's the functional groups little pop quiz on the survey this morning. And note that it says which functional group is not in this molecule. So if I'm looking at it, the answers that I'm seeing from y'all so far, there are only a few submitted. I'm seeing that there's not a hemiacetal. I'm seeing there's not an acetal. There's not an epoxide. So, drama. So far, no one has gotten it correct in this section for which functional groups are not here. So the most commonly missed one is students see this and say, that's an alcohol. But what do we have to check? Well, is this an OH attached to something else? It's attached to an OR. So what is it called when we have an OR and an OH attached to the same carbon? Hemiacetal. So we do have a hemiacetal in this. We don't have an alcohol. This one over here, that's carboxylic acid, not an alcohol. This one, ether, not an acetal because at both of these points not connected to another oxygen. So again, these are like the functional group traps. You just get better at it by practicing it.
Okay, so ether is the one not with the double bond. Which one has the double bond? Is that ester?
This is the ester, at the bottom. Yeah, it's carbonyl with an OR, and carboxylic acid is carbonyl with an OH. They're all so similar. This feels like the Devil Wears Prada, the like cerulean, like it's just blue. No. So game plan for today is the first 50 minutes or so is going to be spent on the first how to study reactions talk of the summer. There are going to be 3 of these. There are going to be 2 more after this. Basically, I just want to give you more tools for how to study reactions because that's the bulk of the course going forward. Then we're going to spend the last half talking about some of these reaction families up here and kind of getting to know them a little bit more. Any like logistic questions before we jump in? Slay. So, you want to study reactions. How should you focus your studying? Well, this is a class. You get grades. Let's focus on it by talking about the ways that you are going to be tested on reactions. So, the last 3 pages of your 9-page exam will all be focused on reactions. And we are going to get to know the different types of problems that are asked about reactions here. So again, knowing how you are tested is going to help clarify your studying. So starting off with a reaction, we have the line reaction. The line reaction is listed all essentially on one kind of horizontal line. You have some starting molecule. You have an arrow that has some other reagents or solvents or reaction conditions or whatever. And then you have a product. So the first way that we can ask about a reaction is asking about these line reactions, and we call these problems box problems. They are the easiest questions to write because all we do is we take one of these 3 parts and we just put a box over it. So we could put a box over the product and be like, okay, what's the product, given the starting material and these reagents? Typically with box problems, we're going to have like between 2 and 4 steps of reactions here. So these might be like 2 separate whole reactions, like this is one separate reaction and this is another. But yes, we can ask you predict the product. That's kind of the classic way. The second style is the whodunit. We can cover up, okay, what reagents do we need to use to accomplish this goal? And then hard mode is thinking backwards, where we give you the product and the reagents and you have to predict the starting material. So box problems, this is going to be 1 page of your exam, and you're going to have like 4 or 5 of these on it. The second type are mechanism questions. This is the curved arrows. So we said that we have the line reaction component of a reaction, and the mechanism is like all of these arrows. And so 1 page of your exam is going to be a mechanism question where you're going to have to do all the curved arrows, all the formal charges, all the intermediates, things like that. Also fair game for mechanism question is asking about homo-lumo interactions and like donors and acceptors. For mechanisms, there are kind of 2 flavors of questions that we ask. One is a known mechanism. Known mechanisms are basically regurgitation. It's like, okay, you're going to be drawing the exact same arrows that were in another problem. We're going to like change the R groups, like the carbon chains, but the functional groups and the curved arrows exactly the same beat for beat. So known mechanism questions, that doesn't sound very interesting, right? And we don't want to just test your ability to regurgitate things. We want to test how you can think in this chemical space. And so we can do things to make known mechanisms harder. One thing that we can do is we can stack multiple mechanisms together and like say, okay, do this reaction, then do another reaction, and just draw the full mechanism of it. We can have you do like a reverse reaction and then a forward reaction of something else and do the full curved arrows. We could start in the middle of a mechanism and say, okay, finish doing this and then go on and do another reaction. But known mechanisms are the ones that feel a little bit safer. The hard part is just recognizing what's going on, what is the reaction. A new mechanism question is, we're not throwing you to the wolves. It's not going to be something you've never seen before. It's going to be 90% similar to something you've seen that we have taught you directly, with maybe 1 or 2 weird steps. And an example of this is in one of the challenge problems on PSET 2, one of the last challenge problems. It has a new mechanism where there's like 1 step that's kind of weird, but the rest of it is totally similar to something that you've seen before. So again, we won't throw you to the wolves on it, but we want to make sure that this mechanistic logic that we are teaching you in these reactions is becoming internalized so that you can apply it to new scenarios. Because eventually we want you to be where we present you with molecules and we ask, like, how do you think this would react, even if it's not a reaction that we've taught you? And again, that's pretty far away, but the new reactions for the test will only have 1 or 2 changes. So we have mechanisms and we have box problems. Now, one thing I want to say is box problems and mechanisms, each of these is going to be 1 page. And it's 90 minutes for a 9-page exam, so each page is about 10 minutes. So box problems, you have 10 minutes to do 4 or 5 of these. Do you think you have enough time to write out all of the mechanisms for all of these? No, not at all. So there is a separate skill going on here of how do you just write the product without having to think through the mechanism. And like knowing that that's how you're going to be tested and that's not feasible for you to just try to quickly think through the mechanism on a box problem means that we have to tailor our studying to specifically study line reactions for these box problem questions. And that'll come into play when we talk about the study method. The last type of question is the hardest type. And for the Harvard College students in the room, I'm so sorry. This is something where if you took Chem 17 in the fall, they are not tested on synthesis at all. This is something that's only in the summer version, and it's because the summer version is to prepare students to go into either 27 or you can go into Chem 30 after this. So this is something that the chem majors do. It's also something that's done in every other major organic chemistry sequence across the country, and so for students doing it from other universities, we think it's an important part to include here to see in the summer. So the concept of a synthesis question is, we give you a starting molecule, we give you a product molecule, and we say in 8 to 10 reactions that you've learned, build the product from the starting material. So it really is like, have you seen the kind of like hierarchy of learning where like the low level is just recall and then, or like recognize, recall, evaluate, analyze, whatever. Like there are all these like verbs that you can do that's test how deeply you have to learn something. The top level of that is to create. And this is really like thinking of reactions as little Lego blocks, and we're asking you to build a little like art piece. So it is like you have to know these reactions really well so that you can like start to think in that space. And it's like a brand new game and you're not going to be good at it right away. This is an example of like an exam 2 level synthesis. So this exam 2 synthesis is going to be like 8 to 10 steps. Or 8 to 10 reactions, and then the exam 1 is only going to be 4 to 6 because you don't know that many reactions yet. But one thing that you'll note, your answer is just kind of repeated line reactions, one after another. So there are no curved arrows on this, and in fact, you can't get any points on a synthesis question for curved arrows. It's only for reagents and intermediates. So 1 page of the first exam will be a synthesis. Questions on how you are going to be tested on reactions. Yeah?
For the synthesis questions, if we were to draw the curved arrows just to like help us think through, would we lose points for that?
No, but I was going to say the most respectful way I can say this, but it's kind of sassy. A sassy way that I can say this is if you are drawing curved arrows on a synthesis, you're dead in the water. Like, that, it's not what it's about. And like you will only confuse yourself more by doing curved arrows, even though we think it's helpful. Because you are learning this, we're wanting to teach you the principles of reactivity, kind of building it from the ground up. So you think, oh yeah, I can use arrows to reason through it. But this is such a high level of putting the pieces together that it would be like, instead of using Lego blocks to build a little like cat or something, it would be like, so what's a Lego made of? Do you see how it's just like a different way of thinking that's going to distract you from playing this bigger game? So we're going to talk about how do we study given that as like one of the criteria here. Yeah. So before we do the study method, I have some general advice. So one is the importance of practice here. And I know you like hear, okay, practice. But I think a lot of people, me included, like to think of homework and practice problems as like a test of your mastery. Like you study something first, then you do the practice problems. And like, because you studied, it makes the problems easier, and that's like nice. Because of the time constraints of this class, that's kind of a luxury that we can't really afford. Like if you wait until you fully understand lectures 3 and 4 to start doing the problem set, like if you study and do like your copying lecture notes and doing this kind of studying that feels good, you won't be starting the problem set really until maybe Sunday night, and then at that point you're screwed because the PSET's due in 1 day. It's also the thing of, let's say you studied all the lectures, the first 4 lectures, super thoroughly. You did, again, your review sheets or notes, or you rewatched all the lectures or whatever. If you did all of that and don't take the practice exams, I think the max score you would get is a 70. Like, practicing and doing these working problems where you do not have the answers in front of you are crucial in order to do well in the class. And so the thing I'd like to encourage you to do is, like, think of the practice problems as a tool for learning and studying rather than a test of your mastery. Like, use it while you still have incomplete information to point you to what you do not know. Use it as, like, you have to just kind of be doing it all together. You can't do this, like, idealized studying because, especially in the summer, there's just simply not time. The challenge of organic chemistry is how quickly can you digest a new batch of reactions? Because every lecture going forward, other than lecture 4 is kind of its own, like, little separate topic. Every lecture, we are just going to be throwing 8 to 12 more reactions at you. We are going to force feed your reactions for the rest of the course. And the rate limiting step to your success in organic chemistry is how well can you integrate these new reactions into your mental schema and get to where you can use them for these types of questions, for synthesis and box problems and mechanisms. Like, the faster you get at taking in a new set of reactions and knowing them cold in your blood, the better you do in the class. Like, again, if you are having to spend time, you have 10 minutes to do a synthesis. If you're having to spend those 10 minutes remembering things rather than just, okay, I know the things, how do I put them together? Like, you're not going to be able to do the synthesis, you know? Like, it would be like trying to play chess, but then not knowing how all the pieces move. Like, you have to go in knowing how all the pieces move. Yes, also, all of these reactions are cumulative. By the end of the course, you'll have over 100 reactions, and you'll be doing synthesis and mechanisms and box problems. So that's the challenge. Like, that is why OChem is a scary class. You now can see it. And you're going to get better. You're going to practice it, and we don't throw you into, like, the worst of it initially. Remember, we start off kind of baby steps, but by exam 2, it's kind of beefy. Another metaphor is reactions are tools that accomplish specific chemical goals. So if we think about teaching you all these reactions, you can list them off in, like, a long list, like a numbered list from 1 to 100. But it would be like having a toolbox where your tools are just there and not organized into different compartments or sections. And so one thing that is going to be really important as we start to get more and more reactions is not only do you need to know them, you need to have an organized way of grouping them in your head so you know which area of the toolbox to reach for. And the biggest strategy I use for this are reaction families, which we're going to talk about the reaction families of lecture 3 later on. But having kind of an organized toolbox. Any questions before we actually jump into the study method and kind of see it in action? I don't feel like I've alleviated fear yet. Hopefully the studying and going through the reaction together on the next page will lower fear. So what I want us to do is, if you have the section notes, make sure you have this page up. And if you are a print user, if you can get out the page in lecture that does the acetal reaction. I believe it's on page like 55-ish, somewhere around there. But we are going to be kind of trying out this study approach with the acetal reaction, which is the longest and scariest reaction that you will have on the first exam. So the key idea behind this kind of study method, which I use, I didn't come up with it. I've just kind of like written it all down. But the key idea here is, in order to really learn reactions to answer all these different types of questions, you need to be studying and thinking at different levels of detail. So I'm going to kind of walk through these different levels with you, and we're going to do analysis studying of the acetal reaction, so that by the end of it, you should feel like we've beaten a dead horse and you actually like know the acetal reaction more, hopefully. But let's start off with the most detailed level. It is the full curved arrow mechanism. You remember, the mechanism question is the most detailed question that we can ask you. Not necessarily the hardest, but it is like every curved arrow. It's HOMO, LUMO, donor, acceptor things. And the warning that I'll give here is a lot of students do this. This is the first thing that they do with their studying. But if you only study this, the rest of it won't magically congeal. Studying mechanisms will not make you good at box problems or synthesis. And so we need other tools. The other kind of warning with doing a lot of studying for the mechanism is I see students kind of approaching it in a way that's very time intensive. Writing out a full mechanism takes a lot of time, and it's just not pragmatic to be like writing a mechanism over and over and over. And so we need some other tools to kind of like zoom out, save some time. And that really kind of takes us to the second level, mechanistic logic. So what we're going to do with this reaction is we are going to go through each step, and we're going to try to summarize what is happening in plain English. Because right now, like this full mechanism, most detailed level, this is a lot of visual information, and respectfully, y'all don't have much experience studying visual information. You have a lot more experience studying words and lists and like learning algorithmic approaches, right? Like you just have more practice. So let's try to translate this visual stuff into words. And when we are doing this, the other thing that we want to do, analyzing this reaction, is ask ourselves why. Why are we doing this step? What is it accomplishing? What are the details here that like we could like have an answer here of a mechanism and get full points, but it doesn't help us understand why we are doing the things that we are doing. Like we want this to feel less like you are just doing random things because we told you, and more like you are understanding this is the movement of electrons because of how molecules want to react, and like knowing the why. So let's start off with this first step here. Can someone help me like translate this step into English? Protonate. And I'm just going to say we protonate the carbonyl. Cool. Why?
To make the carbonyl carbon a better electrophile.
Yeah. So maybe to help answer that, let's look forward to the second step here. How can we summarize this step in English? Yeah, and can you be more specific?
The oxygen on the ethanol attacks the carbonyl carbon.
Yeah, now I'm going to be picky. I'm going to be like, let's be less specific. Because, again, the whole purpose of this is we want to get something short, that quick is to the point, but also something that has enough information such that if we only had this, we could draw exactly what we mean. So thinking about kind of a middle ground between those, maybe I would say an alcohol nucleophile attacks a carbonyl electrophile. Do you think that that's enough information that you could draw both of these arrows? For example, like if I told you an alcohol was a nucleophile, do you kind of know that the lone pair on the oxygen is the donor for an alcohol as a nucleophile? Yeah, y'all have done some practice with this now. And then if I said a carbonyl was electrophile, are you thinking about the pi star CO? And then if you put electrons in an antibond, what happens? The bond breaks. Thank you. Great. So if we go back to this protonate the carbonyl here, the reason that we do it is, do you remember when we were talking about like in a reaction, there is a HOMO of the nucleophile, LUMO of the electrophile, and the energy gap between them, this HOMO-LUMO gap, kind of determines whether a reaction happens or not. If you have a really big gap in energy, these things won't react with each other. And so what we want to do is make that gap smaller. There are two ways we can do it. We can raise the energy of the HOMO or lower the energy of the LUMO. And here, by protonating the carbonyl is the electrophile, right? So that is an example of lowering the energy of the LUMO. Okay, why does protonating the carbonyl lower the energy of a LUMO? Yeah.
Because it gives the oxygen a positive charge.
Why? Why does that lower the energy of the LUMO?
Because giving it a positive charge, actually I don't know.
No, you're close. Anyone else?
Is there less repulsion? Like less electrons?
Y'all are dancing around it, yeah. So having a positive formal charge is one of our low energy trifecta that lowers the energy of an MO. And the actual reason for it is because when you have a positive formal charge, you're holding on to the electrons even tighter. You really want the electrons, and it's creating a more favorable like Coulombic attraction between the negative electrons and the positive nucleus. And so like we don't need to explain that every time, but we need to know that like, oh, okay, protonating, putting a positive charge, lowers the energy of the LUMO, makes it a better electrophile. Like that's the quick, accessible version of this. So let's like write that down. So the Y of this step is to make the carbonyl a better electrophile by lowering the energy of the LUMO, which in this case is a pi star CO. And then by that same logic, if we're kind of zooming in on the details here, we can write for the next step, we have our donor as lone pair on oxygen attacking the pi star CO. Okay. Then I'm going to group the next two substeps together. So can anyone help me out with the description of these steps? What are we doing? Yeah.
Deprotonating.
Yeah, we deprotonate here. And then what are we doing here?
Deprotonate.
Yeah, we're protonating but in a different spot. So these two together we call a proton transfer, which eventually we are going to let you abbreviate these steps and not draw the curved arrows, but the first exam you do have to draw it. Now, one note here, I don't think Logan used this abbreviation in lecture. So SOL just stands for the solvent. And that's just saying some molecule in the solvent is going to come and take off a hydrogen. I think Logan specifically listed another equivalent of HOET is going to come along, but this also works. We don't care about the identity of this. We care about our growing molecule that we are making. And you might see him use this abbreviation later on in the class. It's kind of like how we use H plus instead of H3O plus, things like that. Okay, so we're doing this proton transfer. The other thing I'll warn you with this is a lot of students will try to do this and do them at the same time, and this just does not happen. The hydrogen that gets added over here is not the hydrogen that was taken off initially. These are like separate hydrogens. Hydrogens, typically acid-base stuff, is fast. They fly on and off. And also just geometrically, it's not going to be able to reach because that would be a strained four-membered ring, and so it's going to be hard to do that attack. Okay, well, maybe to help answer the why of this step, let's look at the next step. So, what was this step called? The lone pair push, LPP. Great publicist. Her publicist deserves a raise. And specifically, because we want enough information to be able to do this step without seeing the molecule, I'm going to say we're going to lone pair push off water. Now, the lone pair push, I think Logan downplayed it a little bit. She's the cinematic moment. She is the drama. She is the climax of the film. She is the ooh-ah sensation. She is 4 friends sharing an apartment in Brooklyn, and one day Rebecca says, "James, I've had enough of your shit. Get out." And then pushes James out of the apartment, and suddenly the 4-person apartment becomes a 3-person apartment, and everyone's happier. Drama. Like, you're going from 1 molecule to 2 molecules. Like, what? We're breaking a sigma bond. This is the only time we've seen a sigma bond break other than acid-base. She's powerful. Lone pair push. Yes?
Are there certain, like, is H2O common to, like, break off?
So, yeah, we're going to talk about that in a second. Yeah, great. So, we're lone pair pushing off the H2O. Can you help me out with donors and acceptors here? So, what's our donor? Work. I appreciate y'all so much. Y'all are my most responsive section, and it makes a world of difference. 9 a.m. it's pulling teeth. And it's pulling teeth, and I'll get... Like, commit, even if it's wrong. I love it. I appreciate it. Great. Okay, and then we're breaking this sigma CO, so where did we put electrons?
In
the antibond! Yes. Oh, my gosh. Sigma star CO. Beautiful. So lone pair push is the cinematic moment. How does that make us kind of like think about these steps? Because these steps really are leading up to the cinematic moment, right? So how does the proton transfer make the lone pair push possible? Any ideas?
It gives oxygen a positive charge.
Yeah, so let's think about this. If we were to just lone pair push from here and kick off OH, OH is a pretty bad leaving group because it's negatively charged. It's not going to be very stable on its own. And so I liken this step to, in the apartment metaphor where you're kicking someone out of the apartment, this is packing their bags for them, making it so that when you push them out onto the streets of New York, they have their suitcases packed rather than strewn everywhere. So this makes into the OH into a better leaving group. So make OH into a better leaving group.
Will OH ever leave by itself, or does it have to be changed?
There are certain contexts where it will later on in the class, but it is notoriously a bad leaving group. We are going to teach you a whole set of reactions for how to make OHs better leaving groups because they are so bad. So I would just instill now, OH, bad leaving group. Okay, and then how does the deprotonation part help for our lone pair push?
Gives the oxygen.
Yeah. So let's think about, okay, what if we just do the protonation and then try to do a lone pair push from here? Well then, this oxygen would have 4 bonds on it, which would give what formal charge? 2 plus. Nar. She's not going to do that. What do you know? So the reason for this deprotonation is to set up the OET to be the lone pair pusher. Yeah, I like to think about a lone pair push. The 2 main players in it are the lone pair pusher and the leaving group. And just like when we talk about like homo-lumo gap, we can raise the energy of the homo, lower the energy of the lumo. Here, we can make something a better lone pair pusher, and we can make something a better leaving group. And that makes this step more likely, you know? Yeah.
Does the oxygen having a positive charge like make it easier to push out?
Yeah.
Because of, like, electron affinity?
Yeah, well, it's less about electron affinity and more about when you kick it off. Here it's a neutral molecule. It's stable. Versus if you kicked off OH minus, it is unstable. So does OH minus want to leave?
No.
No. Yeah. Cool. Okay, step 5 here. Can you help me translate this into English?
Same as step 2.
Ding, ding, ding. If we scroll up, what do we see? Look at these arrows. Do you agree these arrows are exactly the same?
Yeah.
I'm just going to copy and paste her. Alcohol, nucleophile, taxocarbonyl, electrophile. Patterns, insights, reasoning. Wow. Maybe there will be common patterns among different reactions too, and it will make learning all of them easier. Just a thought. Okay, last step. What's going on here?
Deprotonation.
Yeah, and why do we do it?
To make the oxygen neutral.
Yeah, like our final product is neutral, and like neutral things are more stable. So neutralize product. Now we could do homo-lumo things for all the acid-base steps, but the acid-base steps I don't think that we need it as much because it's always a lone pair donating into a sigma star H something. You know, like at this point, y'all kind of know acid-base arrows and MOs. So, okay, it seems like we've taken already a lot of information and made even more information out of it. And like we might understand it a little bit more, but this still doesn't make this less overwhelming. And so one thing that we can do once we have these is we can start to notice some patterns here. So, for example, steps 1, 3, and 6 are just acid-base, right? Steps 2 and 5, these are an alcohol nucleophile attacking carbonyl electrophile, a nucleophile attacking carbonyl, which is the core idea behind lecture 3. Nucleophiles attack carbonyl electrophiles. And then the one other different type of arrow we have is the lone pair push. So even though we have these 6 or 7 sub-steps, we only have 3 core types of mechanistic logic: acid-base, nucleophile attacking carbonyl electrophile, and lone pair push-off a leaving group. And those are really only the 3 moves that we teach you for all of lecture 3. There's technically like one other type that can happen with an enone, which we're going to talk about in a bit, but like every other curved arrow you drew in the lecture is one of these 3 types of things. Even as we go on to whole other lectures, this list of mechanistic logic is actually going to stay pretty short for the whole course. Like I think for the entire class, you're only going to learn like 15 to 20 types of arrows, and that's going to generate like 100 reactions. So if you think about it as like all of your steps have to be one of these 3 things, you can start kind of tagging and coding these steps when you are studying. Furthermore, because we've translated this into English, we can make a list. And I know y'all are good at studying lists. You can make a flashcard with steps of, okay, for the acetal reaction, these are the 6 steps I need to do in this order. And then based on just this, try to see if you can write out a full mechanism where you don't have like all the curved arrows in front of you. Is this enough for you? Then try to see, okay, can I like think acetal reaction and write down these steps from memory and then do the curved arrows? Like it becomes another tool that you can study with, another way to organize this information. And this is way more wieldy than like the whole full curved arrow mechanism. The other thing that you can do when you are studying, yes, on the exam on a mechanism question, you need all the curved arrows, you need all the steps. But at some point, you will trust yourself enough to know, I don't need to draw the protonation. Like, I know I can do the protonation on the test. I know what a protonation looks like. I don't need to draw it. Drawing out all the proton transfer, I know I need to do it on the test. But it's going to waste my time studying to just, like, keep writing it over and over if I know how to do it, you know? It helps you, like, isolate which steps you actually have trouble with, arrows-wise, and which steps you do need to keep, like, writing out until it, like, clicks. So that is the first 2, the kind of most detailed 2 layers of studying these reactions. Let's take it another step higher. So remember, we said box problems, we don't want to be thinking about all this mechanism stuff, right? We want to be able to just, honestly, within 10 seconds, draw the product of any reaction. That's a separate skill that, yes, is connected to all this, but we need to treat it as a separate skill. So, a few things. At the line reaction level, we are going to analyze this in terms of functional groups. Anytime you see box problem question, you should be labeling functional groups in starting materials and products. So over here, what functional group do we have? Aldehyde. And this could also be a ketone. So I'm going to do an aldehyde or ketone. What functional group's this? Alcohol. Great. And then functional group on our product, this is the acetal reaction. It better make an acetal. And then also we are in acid. So that's a reaction condition to be important. And so one thing that we should be thinking about is if you see on an arrow a ketone, an alcohol, and acid, that needs to become, oh, this is the acetal reaction. Like there needs to be a clocking of if we see these functional groups together, it's going to do this reaction. If you see an MgBr, that's the Grignard reagent, we're doing the Grignard reaction. Like there needs to be a tagging to identify where we're at. So now, I'm going to advocate for a tool that's a little controversial that I call the fake mechanism. So the real mechanism is about like chemical reactivity. It's like all the curved arrows and everything, and it like comes from a conceptual place. The fake mechanism is you have a smooth brain. What are molecules? I do not know. So the fake mechanism is drawing instructions for simply how do you draw the product from the starting materials. So what I'm going to do is I'm going to look at the starting material and the product. I'm going to look at, literally spot the difference. What's the same? What's different? And I see this whole bottom part is the same, right? So the first step of my fake mechanism is going to be erase the carbonyl. So literally like eraser, not based on mechanistic logic or anything, but just she's gone. And what do I need to put in her place? I need to put 2 of these, right? And where did this come from? Well, that's this guy, right? So if an alcohol is ROH, where R is some alkyl group, the thing that we are adding are 2 of these ORs. And I guess the H just like falls off. Fake mechanism. I don't care how it falls off. I just need to be able to draw the product. Okay, so like if this was MEOH, what I would do is erase. I would do OME, OME. Done. 5 seconds. You have the answer to a line reaction. And especially on box problems where we'll have 2 or 3 reactions, you need to be able to just draw the intermediate after the first reaction so that you can start to think about the next part of the box problem. So can you try it out with this little example here? Like I'm going to give you like 15 seconds. Literally do fake mechanism, erase, add the ORs, see if you can draw the product. So first thing I did, I just erased the carbonyl. Second thing, I need to figure out what the OR is, right? So here, this is going to be our R group. I see it has 1, 2, 3 carbons. So I'm going to put O with 1, 2, 3 carbons. That's the OR. Then I'm going to put another O with 1, 2, 3 carbons. That's it. Now, if it's a reversible reaction, you also need a fake mechanism for the reverse. So you would come up with a way, okay, I erase the 2 ORs, and then I put a carbonyl on. But like literally this heuristic, this shortcut, is going to be invaluable for doing box problems. Again, if you are doing mechanisms on a box problem question, you're a little bit dead in the water. So sorry. Any questions about the fake mechanism or the line reaction level here? Yep.
Do those steps of the fake mechanism apply to like all line reactions or just?
No, just this line reaction. Like there is a specific fake mechanism drawing instructions for each reaction.
Okay.
So like, for example, for the Grignard reaction, my fake mechanism would be erase the carbonyl, add an OH, and add an R. And you're just going to need like a shortcut version for all of them.
Okay.
And even if it's not a reversible reaction, it's worth having a shortcut to go backwards. Like if you are at this, you need to identify what the R group is and erase the OH and put a carbonyl. Because remember, we can ask you to go backwards. Even on irreversible reactions, we can ask you what the starting material was. So really just kind of building fluidity with that. Yeah. Other questions on line reaction? Yeah.
Well, just for that one, like, is like the H, like, is that just to get rid of the H in alcohol? Like, why is it the, like, when we see the plus in, like.
In acid? So this is just one of the reaction conditions. And why is it important?
Sorry, like, down below when we're doing the fake thing.
Yeah.
Like, should we just assume that, like, that gets rid of, like, the H and the O in the alcohol?
So
Like, why is that, like, I get why it's there, but, like, when we're doing our fake thing.
for fake, we don't care about why.
Okay.
For fake, it's literally drawing instructions. Because the why, we are going to test you on the mechanism.
Yeah.
Why do we need H+? We need it to protonate the carbonyl to make it a better electrophile to start the reaction. And so like the actual why is answered by the real things of the mechanism. Fake mechanism is literally a shortcut tool for you that makes box problems survivable.
Okay.
Yeah. Mm-hmm.
If we have a question that's not asking for a full mechanism and it's just a line reaction, can we just do the fake part and get?
You should. We will not give credit for curved arrows for a box problem or a synthesis. Yeah, literally. And the thing is, I've seen so many students waste so much time on exams and not get any points because they're trying to do curved arrows. And that's why I'm like a little like, I feel fanatical, kind of being like, no arrows, fake mechanism. But like, I want you to get points. Okay, let's do the last level here, the highest order of thinking. So this is talking about reaction goals, purpose, and generalizing reactions. So let's start with purpose. The purpose of a reaction is answering the question, why are we having you learn this? Why did some grad student or postdoc spend years of their life developing this reaction? And generally, the answer to the purpose question is always going to be to go from some functional group to another functional group. That is what we are doing in organic chemistry. So for this reaction, the acetal reaction, I'm going to add a little bit more specific language here. I'm going to say it's to reversibly interconvert between a ketone aldehyde plus alcohol and an acetal. So like this being a reaction that's reversible is going to be very powerful when we start to think about syntheses, where we want to maybe do a reaction with another part and come back to it later, you know? You can turn a carbonyl into an acetal, and then later on you can take it back to a carbonyl. Like that being a strategy you can use, and the chess metaphor is like castling, of like the advanced moves that you can do with your rook or something. But you can only do that once you know how all the pieces primarily work. So yeah, we're doing functional group interconversions. And maybe from that, let's do a generalization. So when we teach you reactions in class, typically we are teaching you a specific reaction as an example. Like this one is specifically with ethanol, specifically with propanol. And this reaction works with any alcohol, any ketone aldehyde. So like I could put whatever I want here, blah, 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 and it's the same reaction. This is the whole generalizing why do we use functional groups argument. And so one thing that's helpful for us is to get what are the most general way that we can write this? What is the most general way we can write this? And so for ketone or aldehyde, I'd write it like this. So we either have R's on both sides or R's and an H on both sides. Then we're using an alcohol, which I might do R prime just to say this is different from whatever is on the ketone aldehyde. And we have H plus. And then our product here, we keep the base of it the same. And then we have two OR primes. So that's kind of the most general way we can see this. And we can imagine that like any acetal reaction we ever see will fit into this template. And this is just a more concise thing to study, you know? Now, lastly, goals. I like to think about SMART goals that are actionable and very specific and blah, blah, blah. So goals for a chemical reaction are what bonds were made and what bonds were broken. So maybe to start answering which bonds were made and broken, does this oxygen appear in the product? Is this oxygen one of those two oxygens in the product? Do we know just by looking at the line reaction? No, there's no way to know just by doing the line reaction. We have to know from the mechanism. So if we look at it, this oxygen is this, which is the OH, which becomes protonated, which becomes OH2, which is kicked off as water. So we need to break both the sigma and the pi bond here. So our goals, first we need to break the sigma CO and pi CO of our carbonyl. And then we need to make two OETs added, so sigma COs. And when we have these chemical goals, every single step in our reaction should go towards those goals. So, for example, either it's accomplishing these chemical goals or it's setting up those goals to be accomplished in the next step. So, the first step doesn't accomplish either of them, but it sets up step 2. And step 2, it breaks the pi CO and it makes one of the OET added. So it accomplishes half of our goals in one step. Proton transfer, does that do any of the make or break goals for us, or is that a setup step? It's just setting us up for other things. The lone pair push, what does that do? Does it break one of the bonds that we need or make one of the bonds that we need?
Yeah, gets rid of the ones we don't.
It breaks that sigma CO that was originally in the carbonyl. So that accomplishes our last breaking step. And then finally, step 5 is where we do our last making step. So we make our OET added. And the last step is just kind of a consequence to make it neutral. But again, if we have these goals of what bonds we're making or breaking in mind when we are studying these reactions, then everything in our mechanism should support those goals. So, with this, I'm hoping, at this point, the acetal mechanism you should be a little sick of. We spent a lot of time thinking about it. Does the acetal mechanism feel less scary now? Kind of? It's still a little scary. Do you feel like you understand a little bit more of what's going on? That's a process that you're going to have to do with all these reactions, but luckily, this is the only really long one. The acetal reaction and the reverse reaction are the only ones that are 6 steps. All the other ones are much shorter. And one thing that I have done to try to help you with your studying and to kind of model what this looks like for a set of reactions is on the last page of the section notes, I made a reaction summary sheet for all the reactions from the lecture. And in each of them, I go through, I've generalized the line reaction. I've written out what the steps are in terms of just the logic of them. Anytime there's extra bonus information about how does it behave with enones or esters or when do you not need a mechanism, I've written them out. And I've also done this kind of helpful organizational thing, which is to group these reactions into reaction families. If you were to just list out all 10 of these reactions, it's going to be your unorganized toolbox where why are some of these together or not? We really have 3 big families. We have the organometallic reactions, and a reaction family is brought together by having a shared purpose. So the organometallic reactions, their whole purpose is to add an alkyl group to a carbonyl. The hydride equivalent reactions, the whole purpose is to reduce a carbonyl to an alcohol. And then the last one is the reversible carbonyl additions, which is to reversibly interconvert between a ketone aldehyde and another functional group, which is where we saw our acetal. And so this process of making a study sheet for reactions, you can use mine, but it's kind of a trap. Part of what will let you learn these reactions and really internalize them is you grappling with the reactions as they're presented in lecture and organizing them for yourself. I would say even when I was teaching this, I don't feel like I really knew these reactions cold until I had to make this, until I had to organize it for myself. There's one other reaction that's just a little bit weird and doesn't fit into the other families, which we're going to talk about explicitly in a bit. But again, I want you to have this to model what studying reactions looks like and how to kind of organize it. So with that, why don't we take a break for a couple minutes, stretch your legs, check your phone, shake it off, and then we'll come back and we'll talk about some of the other families. Jack. Joseph. First letter. Josie? No. J. I'll think on it. You're Josie. In pink. First letter. Hammy? Yeah, it worked. I need to update that. And what's your actual name? Emily. Okay. I'm going to put that on my spreadsheet so I know. We decided. There is another Emily. Do you spell it Hammy when you go by? Okay, work.
can fit so close, no more than a stone's throw. Looking for a window, but you're the wall that I keep banging my head against. I'm always saying this time I'll get through. I end up with a
Okay, 2 minutes. Let's jump back in. So, because we spent so much time talking about the acetyl mechanism, I'm not really going to touch on the reversible carbonyl additions at all. The nice thing about all of these other ones is they are much shorter. They're either 2 or 3 steps. So I think that those you'll be able to get pretty easily. But let's start off by talking about the carbanion equivalent family. So the purpose of these reactions is to add an alkyl group to a carbonyl compound. And when we do that, we just so happen to make an alcohol. Making an alcohol here is not the reason why we use these. The reason why we use these is to install an alkyl group. So, like for example, going from a carbonyl, we do go to an alcohol, but the big thing is we've added an R group. We've added carbons. If we wanted to just go from a carbonyl to an alcohol, we do have other reactions that do that, and they don't add an R group. They don't add alcohols. That's the hydride reaction. It's just going from carbonyl to alcohol. So this one, again, the main purpose is to add an alkyl group. I love this meme of the little doggo playing with the tiny doggos, and it's like, no, kiss. And you're just like plugging them. So, setup for this. Why don't we just deprotonate alkanes and make carbon nucleophiles? Well, because, Brenda, the pK is 50. How are we going to deprotonate her? That's crazy. She's unstable. She's not well. So we need things that act like this carbanion, but are actually like functionally like shelf stable. So to do this, we use organometallics. So normally when we have a carbon bonded to something like an oxygen, we're used to seeing carbon with a partial positive charge and oxygen with partial negative. Because typically carbon is the less electronegative one and oxygen's more electronegative, right? But we want to flip the script. We want carbon to have a negative charge on it or a partial negative. And so we need it to bond to something that's even less electronegative than carbon. And what are those on the periodic table? Well, metals. So here the metal is typically either lithium or magnesium or copper. But in these cases, carbon has more electronegativity, and so it has a partial negative on it, making it behave like a carbanion. So with this setup in mind, our 2 main reactions for these are the Grignard reaction with MgBr and alkyl lithium here. So say Grignard with me. Grignard. Never say that again. Grignard. Grignard. Beautiful. So the Grignard reaction here, or the alkyl lithium, they both do the same thing to a ketone and aldehyde. And literally whatever this R group is, gets installed on the carbon that was the carbonyl, and then our carbonyl is turned into an alcohol here. So our mechanism for it is this sigma bond goes and attacks and pushes up on the carbonyl. And when that happens, the metal just kind of sloughs off. Like it's kind of like they're in a marriage and the carbon says, I'm taking the children electrons and leaving. And the metal is just kind of left there blinking. And then the children are now in a new home. So, and we honestly don't care about the metal. Oftentimes we don't even draw it. Like, it's because story mode in organic chemistry is about the carbons. So then, once we've done that, we've installed our alkyl group. We've added our R group. And then we have a negative charge on the oxygen because we pushed up. And so what we have to do is we have to protonate it as a second step here. And that makes our alcohol with our added R group.
Is the R group always going to go like up?
Doesn't matter.
You can draw it wherever.
Yeah, like I mean, I drew it this way to emphasize that the bottom part stays the same.
Okay.
But like you could put R here and the methyl up here.
Okay.
Live your truth, follow your bliss. Now, a couple of features here. So both of these use this solvent diethyl ether, ET2O, which I think of as a little oxygen bat. Oxygen with little wings. And I feel like that's really fitting because Grignard sounds like a vampire.
Yeah.
Yeah. So vampire uses the oxygen bat for the solvent. And for lecture 3, the main types of solvents that you're going to see are either ethers, diethyl ether, Or you'll see an alcohol as a solvent. And so we'll see an example of that in a bit. Also, if you see other organic chemistry resources, this step 2, for our class, we just say acid workup, H+ workup, and we don't care about the specific one. But other classes, they might specifically put H3O+ or H2SO4 or HCl or a specific acid there. We're talking about the same things. Now, we need to know how to make these organometallic reagents. So both of these are made from an alkyl halide, and this is the only reaction that you will know so far that starts with an alkyl halide. So for the exam, if you see an alkyl halide that's doing a reaction, you must have done one of these. So if you add like little elemental magnesium, that's what this 0 means in the superscript. It means that this is just solid magnesium versus like magnesium 2+ the ion. If we shave off some magnesium and diethyl ether with our alkyl halide, magnesium says, mind if I like squeeze in right here, and it makes the Grignard reagent. Similarly, if we just shave some lithium on it, it becomes alkyl lithium. These you do not need to know the mechanisms for. It's a bit above your pay grade right now, and so it's only something that we can use for a line reaction in synthesis. The other thing that I think is a little confusing, so when Logan introduced these, at the bottom of one of the pages it said uses for the Grignard reagent, and it says as a base. And I would like to emphasize that is a distraction case. You should know that these reagents are strong bases, but what we want them to do is not be a base. We want them to attack the carbonyl. The reason why you need to know the fact that these are a strong base is because let's say you have a molecule over here and you have an alcohol or any other hydrogen that's even mildly acidic. Then instead of this Grignard doing the attack you want it to do, every day of the week, it's going to go and just grab the hydrogen over here. And so it's going to do the thing that you don't want it to do. This is why, like, growing up in Georgia, when I took the organic chemistry for the first time, if it was too humid outside, we could not perform a Grignard because literally the Grignard reagent would react with the water in the air. Why do I live in a swamp? I don't know. Call me Shrek. But yes, so this is just the idea that these are bases, these are strong bases, but that's not what we want them to be doing. So we just have to keep an eye out for it. Now, this is kind of the core, Grignards, alkyl lithium. The next things that we are going to do are we are going to talk about kind of variations of this with esters and enones. So are there any questions on this kind of core before we expand it? Yeah.
If the metal just like floats or just like disappears after because it's irrelevant, how do we know whether to use lithium or like?
So between these two, they are exactly the same here.
So you could just always use alkyl lithium?
So, I mean, there will be, there's a reason later why we have the two different versions for enones, essentially. But for, if you're just reacting with a plain Jane, ketone or aldehyde, they're equal.
Okay.
Yeah.
If you're so attracted to the H's, like the strong bases, like how does that work with like an aldehyde that has an H in it at all?
Is that hydrogen on aldehyde acidic? So the aldehyde, like compare an aldehyde to a carboxylic acid. Here, the hydrogen is attached to an oxygen, and then that's stabilized by resonance. That's why this is acidic, has a pK of 5. A Grignard will straight up deprotonate a carboxylic acid, totally. But here, the hydrogen's directly on carbon, and so think of it as almost being at that like pK of 50, like alkane level. So she's just not acidic, actually. Yeah. Great. So let's talk about how this varies. That's a word, right? Varies, thank you. Let's talk about how this varies with esters. So when you have an ester instead of a ketone or aldehyde, and you add a Grignard or alkyl lithium, what you get is double addition of the alkyl group. You get 2 R groups added. And so if we're thinking about our fake mechanism for this one, you would be erasing the carbonyl and the OET. You would be adding 2 R's and an OH. Woof. Okay, why? Why are we doing all this? Well, we start off, and the first step's exactly the same, right? The sigma bond goes and attacks the pi star CO, and it attaches the R group onto that carbon and it breaks the pi bond. But then compare this intermediate versus the one when we attack a ketone. This intermediate here has this OET, which hypothetically could leave. Like you could kick it off, and OET minus is not the best leaving group, but especially when we are in base, a negatively charged environment often, OET can leave. However, in a ketone version, the only things that we have potentially are we can kick off an H minus or a C minus, and those clear. Why am I on that? Like I can't stop. That's my like stem of the past like 2 days. Anyway, so this just has no leaving group, and that's why we can only add the R group once. Once we've got the R group, all that's left to do is protonate it. But when we have a leaving group present, we can do our iconic lone pair push and kick off that leaving group. And what do we make? What's this functional group now? A ketone. So we went from an ester to a ketone in the middle of the reaction. Crazy. And why doesn't it stop there? Because we know ketones will react with the Grignard. And so another equivalent, a second molecule of the Grignard, will come over and attack and push up. Now we've added 2. Do we have any leaving groups on this? Not anymore. And so then we move on to step 2, the acid workup, and we get our product where we have double addition. So especially on the first exam, the only real thing that you know what to do with for an ester is double addition. And so almost Pavlovian conditioning, the first thing that you should think when you see an ester is double addition to esters. So like you should like be dreaming about functional groups, and like then like a mysterious message comes to you and it's double addition to esters. And like you wake up and you're like, I know what I must do. You should be in line at the coffee shop and it's like, I have a latte for ester, and think double addition to esters. Like Pavlovian conditioning. Okay? Yeah.
When you have like something like an ester, in that case, would you not need to like do any protonation? That at least already has like.
So eventually you will need the protonation at the very end to quench the reaction, to stop it. But here, because this O minus is going to reform a carbonyl, you actually want to keep it as an O minus to be a better lone pair pusher.
Okay.
Yeah, because O minus is going to be a better lone pair pusher than OH.
And that's the same for the first step as well.
What do you mean? Oh, why we don't protonate it?
Yeah.
Why we don't protonate it here is the Grignard and alkylithium are strong boys. They are really good nucleophiles. They are so reactive. They will attack whatever.
It happens immediately, they don't even.
Yeah, whereas ethanol? Ethanol is basically water. Is water very reactive? No. God, I need to stop. But yeah, that's a great question. And so that's why for the acetal we need an acid to protonate it to make it better, because we have bad nucleophile.
Okay.
Yeah.
Also, hypothetically, if you were to try to like protonate the oxygen, wouldn't the acetal just like take it off?
Are you talking about in this situation?
Yeah.
If you were to have acidic conditions, this would just do acid base, and it would not attack the ester at all. Does that answer your question?
No, yeah.
So the
That's just what I
numbering-
was thinking. Yeah.
Yeah.
The numbering of the steps is very important, right? Like
100%.
the
Thank
H+
you.
workup is after.
Yes.
It's not
So
in acidic conditions.
if you wrote this, minus 1.5 points. Because if you do not have 1 and 2, you are saying all of this and the starting material goes in the same pot at the same time. Even if it's above and below, if you do not have numbers, above and below doesn't mean anything. Because we can have some things like this is all in one part, above and below, and we mean one pot, right? So if we need things to be separated as steps, you have to write 1, 2. You have to separate them out. That's a great question. Thank you. Okay. This is esters, and again, Pavlovian conditioning. When you hear esters, you think double addition to esters. Wow. Wow. Okay. So now let's talk about the enone problem. Enones are deceptive because you think alkene, ketone, separate functional groups, but we know better. We know better. Why is this one functional group?
Because they're not separated by a sp3 carbon.
In one word, what is it? Resonance. 80% of the time. Yes, you're saying the same thing, but even tighter, it's resonance. So, okay, if we have resonance, we know that this is going to react as one whole functional group. And the thing about enones that's kind of cool is instead of a normal carbonyl, you can just attack the carbon at the base of the carbonyl. For enones, there are 2 potential electrophilic sites. So what we do is we number it from the oxygen 1, 2, 3, 4. And if we attack at the base of the carbonyl, we call that 1,2 addition. If we attack over here at this 4th carbon, the far side of the alkene, this is called 1,4 addition, also known as conjugate addition. Now, I'm going to use one more term here just so that you've seen it, because it sometimes appears in the MCAT, and I want you to have heard it. But basically, whether or not a nucleophile adds to the 1,2 position, the 1,4 position, or is unselective, that's just an inherent property of the nucleophile. And it's kind of something you just have to memorize. Like, the why of it's a bit above the pay grade right now. And so we talk about nucleophiles that only add to the 1,2 position as being hard nucleophiles, and nucleophiles that only add to the 1,4 as being soft nucleophiles. Again, for our class, we are never going to use those terms, but just so that you see it and have heard it.
Could you explain the numbering again? Like,
You start numbering at the oxygen.
why do we include 1 and 2? And not just like 2 addition?
Oh, I mean, that's great. Yeah, it's just convention.
Oh, okay. So it's always going to be 1 and another number?
So yeah, technically the reason is like when you attack it, you move up a charge onto 1.
Okay.
And then if you attack on the 4, you move up a charge all the way up to 1.
Okay.
So that's kind of why. Yeah. Yeah. Cool. So enones present a problem for organometallics because if we do our Grignard, we are unselective. We're going to get 1,2 product and 1,4 product. It tends to lean a little bit 1,2, but you're really going to get a mix. And if we're trying to do a synthesis, we don't want mixed products. We don't want to lose half of our reagent that we've spent weeks in lab isolating or whatever. So lithium is more helpful here because lithium is selective. It's a hard nucleophile. It only adds 1,2, no matter what. So that's why we have the difference between a Grignard and an alkylithium. For non-enone things, it does not matter, but for an enone, it does make a difference. And then also because we want to be able to build whatever molecule that we want, we also want a version that's only 1,4. And that's why we introduced this third one of using a cuprate, which is copper here. Yeah.
When you have the unselected thing, is it like 50/50 is 2 points?
No, it depends. It depends totally on the identity of the molecules, what that ratio is going to be. But generally speaking, you never want to use a Grignard with an enone because you're going to get split. If you're using an enone, we want you to use these. Yeah, great question.
Vampire doesn't care about the identity.
Vampire will suck anyone's blood. Yeah, exactly. So
Isn't there another one with an S?
we're getting to it. So the organocuprates, this is sometimes called the Gilman reaction or Gilman reagent. And it's in this form R2CuLi, where you have 2 of this R group. Now, one thing that's kind of weird is we put 2 of them here, but only 1 is actually added at that 1,4 position. And it's just like notation of how this exists. We make this by taking an alkylithium and sprinkling in a copper halide. But it's just easier to write it like this as one whole thing rather than to write multiple reagents. And also, this way is the way that all of your problem sets write it in the practice exams. Now, cuprates are very selective with how they react. So they do not react with ketones or aldehydes or esters. They only do reactions with enones at the 1,4 position. So they're really specialized. And you are not responsible for the mechanism of this. Logan showed like abbreviated simplistic mechanism, but again, the reality is a little bit more complicated, so you're not responsible for it. With that, let's say we wanted to make this molecule over here from this enone starting material. So to think about how we would figure out what that reagent is, what I'm going to do is I'm going to start with the O and count 1, 2, 3, 4. So those are my original carbons. And I know everything after the squiggle is new, right? So this is going to be my R group that I add. So I need to write R2CuLi. There are a couple ways you can do that. One way you could do it is isopropyl to CuLi. But again, that feels a little bit like, I don't know. It feels a little weird to me. Like, I like being able to actually write it out. You could also write isopropyl Cu Li plus, but I think there's an even easier way to write this. So the way I would write it is whatever you're trying to add here, I would put those carbons, those 3 carbons in parentheses, and then put a 2 by it, CuLi. With that, we use our diethyl ether, and then we do our H plus workup. So there are a few ways that you can write it to do it correctly, but I often see students make mistakes with this because that 2 subscript is a little bit hard when we get more complicated R groups, you know? Cool. So we don't make you learn the mechanism for this. However, we do generally want you to know the mechanism for conjugate addition. And so that's why we had this bonus reaction. This is the one with sulfur. So this is this organometallic? No. Is this adding an alkyl group? No. This is adding a thioether, I guess. Like this is a sulfur version of an ether. So we keep this ketone aldehyde here and we make a thioether. And literally the whole reason why we introduced this was for you to learn the mechanism of conjugate addition. So let's see what that looks like. So what we would do is our thiolate down here, sulfur with negative charge, is going to attack the 1,4 position. Thank you. And when we attack an enone, we are going to push electrons all the way up to the oxygen. So we're going to move this double bond over, and then we are going to move this up. You can think about all the donor acceptor things, but just for the sake of time, I'm going to kind of speed past it. So what we get when we do this is we've added our S with our ethyl at the bottom. We moved a double bond here in the middle, and then we have an O minus at the top. And now, how do we get from this intermediate to the final product? Well, we need to remake our carbonyl, right? But then the second thing's a little sneaky. So if we look at this carbon right here, the carbon that's right next door to a carbonyl is often called the alpha carbon. And you're going to learn that notation formally in lecture 5, so it's coming, so I'm just going to use a term a little bit early. How many hydrogens are on this alpha carbon currently? 1. But if we look at the alpha carbon in the product, how many hydrogens are on it? 2. So a sneaky thing that we've done is we've added a hydrogen. But because we don't have to draw out the hydrogens, it's easy to miss that.
Where did we get it from?
A. That's the question. That's the question. So we need to do an alpha protonation. And an alpha protonation is we are going to push down, reform a carbonyl, and then have this double bond grab an H from somewhere. And where do we have a source of H in our reagents? This alcohol. So this is an alcohol solvent. And do you see how this solvent is actually playing a role in the reaction here? It is a source of hydrogen. It acts as an acid to quench this. And it's a pretty mild acid. We don't think of alcohols as being super acidic. But this is a case where a solvents participate in the reaction, whereas when we had diethyl ether, she never appears once. You will never draw her in a mechanism. So sometimes solvents participate, sometimes they don't. That is the thing to kind of be paying attention to as you learn these reactions.
Maybe they always have to be included, even if they're not.
Yeah. Well, because otherwise, this is an oil and this is an oil, and you're just rubbing oils on each other and hoping that they are going to react fully. You need to dissolve them in a liquid. So that's why we say it's a required thing on the arrows for the line reactions and synthesis. Yeah. So this is the thiolate addition mechanism, the conjugate addition mechanism. And you can see how it's just a little bit one step more, really, with some arrows from our normal attack. So I'm going to give you a few minutes to do some practice here. So these are on page 10 and 11 of the problem set, the skill builders. The first one's just doing this quick little mechanism with a Grignard, and then some box problems. And to be so honest, I would say start off with the box problems because I think they're harder. I want you to have thought about the box problems before we go over them together. But I'm going to give you 4 minutes, so not a lot of time, I'm sorry. Oh wait, yours wasn't tooth crazy. Yours was fries shouldn't be sweet, which is like, yeah, true. I don't feel like meat should be sweet. A sweet meat I'm not here for. Like why? Sweet meat? Yeah, like barbecue being sweet? I don't know. What did I think the crazy one? Oh no. The crazy one was someone like Berry Line sucks. And I was like, that was you. Yeah, no girl. What do you have against Berry Line? Yeah, I didn't realize Ariel has like a cult of personality. She like thinks she's the lost sensation. But really that's not the question.
Yeah, no, I agree with you there.
Okay. It has been 4 minutes, and I still want to talk about hydrides before we go. So, I'm going to do a rapid review. Grignard reaction. We have to draw out this bond. So, if you just started your arrow here, points off. You have to draw the source of your arrows. Arrows are arguments. They need a specific start, specific end. So, we need to draw out that bond. We go and attack the carbon, push up. That makes an intermediate where we have our O minus and where we've added the ET. And then last step, we just protonate this. And we're done. Now, box problems. Remember, the first thing that we're doing when we see box problems is working at that line reaction level, we're tagging functional groups. So what functional group do we have in this first one? Ester. In Pavlovian conditioning, what's the first thing you should think? Double addition, thank you. So, in the product, what functional group do we have? Well, what's the functional group? It's just an alcohol. And we're looking for double addition, right? So do we see something that was added twice? Yeah, methyls. So we added an R group twice, and our R is methyl. So what reagent should we use? Grignard or alkylithium. Either one works. I'm just going to arbitrarily use lithium.
Should we not use it? Did we say don't use a Grignard? Oh, that's right. Only Grignard.
That's only for enones. Other like this, it truly doesn't matter.
Okay.
And if you want to do something that's really fierce, you could write 2 equivalents. And you don't have to. Like, I mean, if you don't include it, I'll know what you mean. But if you put 2 equivalents, you're saying, I want you to know that I know that there are 2 of these. Yeah. Wait, 1 equivalent? Oh, yeah. So these boxes are graded separately on the exam. Yeah, you can't like increase your odds at getting it correct by including more reagents. You have to like make a choice. What? Yes, there's negative marking. Sorry. Yeah, we love to count off. I would try not to. Again, I'm going to be the one solely grading all of your exams. I'm trying to give you as many points as I can, reasonably, in a fair way, you know? What?
Like bring you a coffee on
Oh, sure. Okay, next up, what's our functional group in the starting material? Enone. So not an alkene and ketone, an enone. It reacts as one thing. And enones, we're thinking about 1,2 and 1,4 addition. See how we're flagging the functional group? And then already we're brainstorming because we know facts and the facts are connected to these tent poles of functional groups. Great. Okay, so if I look at the product, the only functional group I see is an alcohol. But the big thing I'm seeing is I've added things. Apparently at this 1,2 position, I added ET, and at the 1,4 I added a pH, which is a phenyl ring, which is benzene, basically. So what should I use for 1,2? Grignard, lithium, or cuprate? Lithium. And 1,4? Cuprate. So I'm going to use ETLI with ET2O, and I'm going to use R2, so our R is pH, 2, CuLi, with ET2O. Okay. So now the question is, should we do the 1,2 addition or 1,4 first? And before you say anything, we're going to do a vote. If you think that we should do the 1,2 addition first, I want you to do a little peace sign. If you think we should do the 1,4 addition first, I want you to do a folded arms kind of moment. So pick your pose. Are you doing 1,2 first, or are you doing 1,4 first? Even if you're unsure, make a choice. Okay, I see some comment. This is the most confident answer I've ever seen. You have a look like, I know. But I see a significant number of 1,2s. Let's try 1,2 first. Let's see. So if I do the lithium first and then the H plus workup, then our product looks like this. If we do the lithium first. What functional groups do we have now? Well, I guess maybe I'll put it another way. Do we have a carbonyl anymore? So can we do any of the reactions in lecture 3? No. We have an alkene, which you're going to learn reactions of alkenes in lecture 8. But, man, pour one out for this path. So these we need to do second, and you were totally right to be that confident over there. This, we are going to do the 1,4 addition first. Slide. Okay, last one down here. Crazy functional groups. We have an ether, and we see that same ether in the product. So did we do a reaction with that ether? No. Do we know reactions of ethers? No. We know ethers as solvents, but we don't know a thing that we can do with it. What's the only other functional group we have here? Yeah, an alkyl halide. Do we know any reactions that start with alkyl halides? Yeah, the only thing we can do is turn it into a Grignard or a lithium. So let's turn it into a Grignard, just cause. That's the only reaction we know at this point. So now it becomes a Grignard, MGBR, with this OME, and this is just a fancy R, RMGBR, right? Now, what functional groups do Grignards attack? Functional groups that Grignards can attack. Carbonyls, ketones, aldehydes, esters, right? So, firstly, I'm looking at this. I'm like, well, this is an alcohol. I mean, I guess technically when we do a Grignard, we get an alcohol, right? And we've added an R group. So, like, this is the new bond that's made. Like, this carbon is not over here. There's no carbon outside the ring over here. And here there's a carbon. So this had to come from some sort of carbonyl compound. So let me look at this. This carbon has 2 hydrogens on it, and it has an OH. And so if we try to turn that into a carbonyl, it would look like this, formaldehyde. And technically, if we're doing a Grignard, we bring the reagents together in the first step, and then we have a second step as an acid workup. This feels deeply uncomfortable. This feels wrong. Because you are used to seeing carbonyl on the left, Grignard on the arrow. But what we've done here is we put Grignard on the left, carbonyl on the arrow. It's the same reaction, we just want you to get used to seeing it both ways. We are going to ask you things like this where you have to supply the carbonyl and you put on the arrow. So it's about getting used to seeing it the other way. If I had written this out as this looks so much more normal, right? Like this is the scheme that you've learned. But we need to be flexible about how we view this because we can ask it so many different ways. So, I'm so sorry. I'm gonna go like 4 more minutes just to give you a bare minimum of hydrides. If you need to go, you can go, but I wanna say like a few words on it. So, the last family that we are gonna talk about is hydride equivalent reactions, and the whole purpose of them is to go from a carbonyl compound, ketone aldehyde ester, to an alcohol. And we do this by adding a hydrogen with its electrons, which we call a hydride. Now, a hydride, you should know, is different from just a H+ proton acid-base stuff. Proton doesn't have its electrons with it. It's not a nucleophile. We need a nucleophile version of hydrogen to go and attack. We could use NaH, which is a strong base, but it is a weak nucleophile. It doesn't like attacking things. And so we need things that behave like a hydride, but aren't. So we use hydride equivalents. These are hydrogens bonded to a group 3A element, typically boron or aluminum. And the reason why we use it is the same reason why we used metals with the carbanion equivalents. We want to make it so that the hydrogen has a partial negative. So we need its bonding partner to be less electronegative than hydrogen. So hydrogen's electronegativity is 2.2, boron is 2.0, and then aluminum's 1.61. So when they are sharing electrons, there are more electrons around the hydrogen. It reacts like H-. So we have 2 flavors of this. We have lithium aluminum hydride, which sometimes we will refer to as LAH, just as a shorthand. And then we have sodium borohydride, the boron version. And both of them have the same exact mechanism, where you use the sigma bond to go and attack the carbonyl and push up. Then you have an O-, you've added your H, and you just need to neutralize it to form the alcohol, and you are done. It's a 2-step mechanism. These are so much nicer after the big acetal and everything. So really the question becomes, why do we have 2 versions of them? And I like to think of them as brothers. And lithium aluminum hydride is the brother that I call toxic masculinity. He's ready to throw hands. He's ready to fight. He is very reactive. He will react with ketones and aldehydes, but also he will react with esters. He will react with things that you don't even know yet. He, super strong, super reactive. And because it's so strong and reactive, we need 2 steps. We need to separate the acid workup step from the lithium hydride, because lithium hydride, if it's in the presence of acid, just like a granular or an alkylithium, it's just going to do acid base. And we want it to actually attack the carbonyl. So lithium hydride, toxic masculinity. Meanwhile, sodium borohydride, that's our soft boy. So sweet, so mild, so gentle. So soft boy, it's weak and mild, so it only reacts with ketones and aldehydes. It does not react with esters. It's also, because it's mild, we can do it all in one pot, in one step. So we can do this in NaBH4, and we can use an alcohol as our acid for this step. We can have like HOMe. And so, again, that's the nice thing about the soft boy. You can do it all in one step. And it differentiates. Like lithium hydride is going to reduce everything in sight. Sodium borohydride can only do ketones and aldehydes. The last thing is, how do these work with enones? So both of them actually are unselective. Both of them will do a mix of 1,2 and 1,4. However, we have an Uno reverse card that we can pull. If we want NaBH4 to, instead of being unselective, if we want to only get 1,2, we can sprinkle in this compound CeCl3, and it will only add 1,2, and will only reduce the carbonyl. This is called the Lusch reduction. Yes, there is a way to only do it 1,4, but we don't teach you it until like the end of lecture 10. So that is the hydride equivalents. Just knowing the difference between those 2 is the only thing I want to make sure you heard. Thank you for coming to section. I hope this was helpful, talking about some of the reactions. tomorrow we're going to dig into stereochemistry, and it's going to be very different and like 3D, and so it's a very different like skill set. Make sure to do the quiz tonight. Scary announcement to come about the practice exams and stuff, but thank you for coming.
Thank you.
Yeah.